Hello and welcome to the next session of Introduction to Biomedical Optics. Today we will try to learn of how do we actually quantify the light, how the light interacts with the tissue. So let us see step by step how do we proceed to that case. Now before we again start from the light interacting with the tissue, let us consider a very simple case where the light interacts with a liquid, a very simple liquid. It could be a translucent liquid, for example a water. So you have light with an incident I naught, and it starts traveling through this medium. Again, it's a translucent medium, and it propagates through this medium with some losses, and then it comes out. Now this is actually a cuvette, and within the cuvette we have filled a particular liquid, and the dimension of the cuvette is small l. The incident light intensity is I naught, that is watt per meter square, and the light which comes out of the cuvette is something like I. We mentioned that is I, that is nothing but watts per meter square. Okay, so now let us try to understand what is transmittance. Okay, now if you see this, what is output is I and our input is I naught. So if you try to intuitively even understand, you will understand that the transmittance is nothing but output by input, right? So it is nothing but I by I naught. Okay, that's just output divided by input. So now let us understand, in addition to this transmittance, because transmittance doesn't give you anything about property of your liquid, right? So there could be another property of the liquid, for example absorption, right? Now if you see absorption which is given by A, transmittance is given by T, absorption given by A, is actually inversely proportional to transmittance. So transmittance is high, your absorption is low, right? And vice versa, it's inversely proportional to your transmittance. So now the absorption is kind of given with the logarithmic logarithmic of inverse of your transmittance. So this is how it's defined. It's a way because in some of the fluids you will see a very low transmittance. Right now, if there is a various significant drop of transmittance, like for example 1 to 0.0001, right, or the transmittance could be as low as 0.000001. So it becomes very difficult to quantify such a low number, right? So that's why people usually use the log scale. So over here as well, for because your transmittance becomes very low. So to overcome the way to define your very low numbers, so people have come with a logarithmic scale. So it's just a way to define. So instead of absorption, I am defining it as 1 over transmittance. Inverse of transmittance, I will tell it log of the inverse of your transmittance, okay, which I can also mention is minus log of 10 with the base 10 of transmittance, and this again actually could be written as, if you substitute the earlier equation, it's kind of log of I naught by I with a base of 10, and if you substitute to the top the transmittance, you can relate it with 10 to the power of minus A, right? So all these things are kind of are the same equation that I am just trying to rephrase it into another forms. Now let us quantify it. For example, you have absorption of 0, right? So that means that so now in most of the textbooks you will find absorption with such values, right? It would be 5, 1, 2, or if you buy any optical components, for example, you will also see such kind of absorption. If you for example, you buy a neutral density filter, right? So you will see an absorption value something like 0, 1 or 2, or it will be an optical density, for example, right? So now if you see an absorption to be 0, if you put 0 over here, 10 power of 0, there is nothing but 1, right? Now if you consider in transmittance, 1 is nothing but 100%. Now if you see absorption is 1, then you have 10 power of minus 1, that is nothing but 0.1, and 0.1 in percentage is nothing but 10%, right? And so on and so forth. If you have absorption of 5, then you have transmittance as low as like 0.00001, right? Which means around percentage wise is around 0.001%, right? So this is how we quantify how much the light is passing through any translucent material, and we assume here, like here the assumption is like the the propagation of light is is still kind of a ballistic, right? Still goes along the same path. The absorption, the diffusion is kind of comparatively lower as compared to as compared to the transmittance. So what you can say is that the scattering is kind of very lower as compared to the propagation, that it's propagating in the same path as the laser is propagating. So this kind of thing more or less you can observe through lasers, because say a laser has a has a very lower beam angle, so it can propagate in a straight path with less divergence, and and can stay in that same path along with a translucent material like what you see over here. Now over here there is an image. I shine a laser and there are three different composition of translucent material. So can you just pause the screen and just try to quantify what would be the value of absorption for all the three cases? Just pause this video and you can just try to see what could be the values of this absorption for three cases. I hope you have thought about it. So what I am doing is I am just shining a laser of 510 nanometers and I am passing through a solution which is having different concentration of rhodamine 6G. So rhodamine 6G is nothing but what do you say? It's a fluorescent dye. So it could be used. So for example, I am shining a laser of 510, and what I'm going to get is a red light. I'm going to get a red light of around 620, for example. Okay, so it's going to be a different wavelength. So if I use a filter which kind of omits my original light source, that is 510 nanometers, then I can only see the red light, that is around 620, 630 nanometers. Okay, so now I assume that I'm only seeing the fluorescent light coming out of it, and you can see that there are three different cases. In the first case is that the light is not able to propagate through much of this, it completely gets absorbed. In the second case is like it's still able to propagate somewhat, but still the kind of you can also see that the light is getting diffused sideways. So, and the third one is you can see the light is able to propagate through this dye which within the cuvette, and you can see you can quantify the values of absorption. So it would be around 5 for the first case, 3 in the second case, and absorption as 1 in the third case. So absorption is the lowest in the third case, and that's why you can see that the laser is able to propagate through this cuvette with a lower concentration of rhodamine 6G. Okay, but so in our case, as we are talking about tissue optics, we are not going to have only a kind of a translucent material or translucent liquid, or not just a liquid, but we are going to have some kind of particles in that liquid, right? So if, as you can see over here, there could be a lot of number of particles, and eventually we are going to concentrate on the composition. We are going to try to find the constituent, what are the different kinds of constituent, and what is the concentration of each of these constituents. That's what we are going to see, how can we find it. Okay, so to do that, to quantify this, we have something known as Beer-Lambert law, which is kind of very much similar to your absorption that you have found. So absorption, which is always also inversely proportional to a logarithmic of absorption is a logarithmic of inverse of your transmittance. Absorption is also directly proportional to the concentration. For example, concentration of rhodamine 6G, as you saw some time back, it was increasing, so the absorption also kind of increased, right? Absorption is also directly proportional to your path length. Path length means the dimension of your cuvette. For example, if your cuvette length is increased to the double of what you have right now, the absorption would also be increased. Right, so it's directly proportional. So what I can come up is that absorption is directly proportional to the multiple or the multiplication of concentration and the path length, right? And that the proportionality constant in our case is a molar absorption coefficient, which is defined as epsilon in this case. Okay, so what you see over here are the units of each of these cases. So you have the molar absorption coefficient, you have the concentration, molar concentration, and then you have the optical path length. So all these things are related with the absorption, directly proportional to the absorption. For example, okay, this is just I am defining what are each of this. So how do you define what is molar absorption coefficient? First thing that you should know that molar absorption coefficient is a function of wavelength. So it's not a constant value along the wavelength. So it actually, if I shine, for example, if I have a rhodamine 6G solution and I shine green light, right, it has a very high absorption, for example, at green light. But if I shine a red light, perhaps it would have a very low absorption coefficient. Okay, so how much strong is this absorption is defined by the molar absorption coefficient, and it is a function of your wavelength. So it has some peaks. For example, for rhodamine 6G, perhaps it has a very high absorption at green light, right? So your epsilon would be very high at green, and then it will die down at other wavelengths, kind of a Gaussian, kind of with a big long tail wiggling, right? So it's again a function of your wavelength, and then you have concentration, that is nothing but moles per liter of a sample dissolved in the solution, and then you have the optical path length, that is nothing but the width of your cuvette. Now, interesting part is that again we are talking about chemistry now, so it's kind of more of chemistry that we are doing right now. And in chemistry, you always see such kind of equation of absorption, which is equal to extinction coefficient or absorption coefficient into concentration and your path length. In physics or in biomedical optics, you might not always see the value of molar absorption coefficient, but you may see something known as absorption coefficient, right? So that is given by mu A, and that mu A sorry, this mu A is kind of given for most of the tissue constituents that are available within your tissue. Perhaps you may not get molar absorption coefficient, but you will kind of get absorption coefficient as a function of wavelength for most of the tissue constituents. Okay, so here you can see that, for example, for absorption, as you see the concentration of rhodamine 6G is increasing from 38 micromolar to around 152 micromolars, and you can see that the absorption also keeps on increasing as the concentration of your rhodamine 6G increases, and it's again a function of wavelength. So it's not a kind of constant thing. It kind of the absorption changes based on the concentration of rhodamine G. Now, for example, if you are aware of this thing, then now you can back calculate. Now, if you have an unknown solution in which you are now able to see that around absorption of around 1, right? So the absorption is around 1. So you can then back calculate and tell how much is the concentration of your rhodamine 6G. That would be a rhodamine B in this case. So if the absorption is around 1, then your concentration of your rhodamine B would be around 99 micromolars, right? So it's kind of back calculating it out and finding out. Now, but this is for single molecule, as you can see over here. It's just for single molecule. You have absorption equal to just epsilon into concentration of concentration into the path length. But what if there are multiple molecules, right? So how do we proceed with such kind of cases? So in that case, Beer-Lambert can be defined for two different molecules, right? For example, the first one, your A by L can be given by epsilon 1 as a function of wavelength into C1, and then you have plus, then you have epsilon 2 as a function of wavelength into C2. That is nothing but you have A over that is the absorption over the path length or this cuvette length is equal to the absorption coefficient of the first species as a function of wavelength into the concentration of the first species, and then you add it with the molar absorption coefficient of the second species as a function of wavelength, and you just multiply it with the concentration of your second species. With this, you can actually find what is this, you can just back calculate again. So once you have a tabulated data, you can actually back calculate what is the concentration of your first species and what is the concentration of second species, assuming that you apply two different wavelengths. So you have two equations and there are two solutions, two unknowns. Okay. Cool. Beer-Lambert law, or what we mentioned till now, was absorption equal to epsilon Cl. Now that is more towards chemistry point of view. Now when you talk about more of physics point of view, there is another way, an alternative form of Beer-Lambert law, which is kind of defined, and that is, if you see over here with a mathematical perspective or physics perspective, you shine a laser through a translucent material over here, and again it has some rhodamine 6b in this solution. And what you see is that if you just zoom into this region over here, you can see that this laser has a very high intensity at the entrance, but it dies down as you go towards the downward regime. And what if you can draw this plot, intensity versus the distance that it is dying down, and you see that it is exponentially dying down. Now what if we can relate your intensity with this exponential curve, and then again can we relate with the concentration of your rhodamine 6b in this case, right? So you can actually do that. So this is your output again. So this is Ix is nothing but the light which is coming out of this sample, and I naught is what you are incidenting. So I naught is the incident light source, and then Ix is your transmitted light source, and then you just multiply the dying exponential function, that is exponential of minus mu a into the distance how much it has traveled, right? So this mu a is nothing but the again absorption coefficient of that particular material as a function of wavelength. Again, this is again a function of wavelength, so very important. Okay, so now either in many of the books you might see epsilon of minus mu a, or you might see epsilon of minus alpha x. Now both of them are kind of the same thing, absorption coefficient. Okay. Now if you see now for different concentration, you will have different absorption coefficient. So you can see that for smaller alpha or smaller epsilon a, the curve would be dying down very slowly, right? And then for some of the other cases, for example, where you have very high concentration of rhodamine 6b, your absorption would be very high. So in those cases, the absorption, this light intensity will die down very quickly, right? Now you want to a way to know what is the penetration depth, right? So usually the penetration depth is defined as at what distance do you actually get the light intensity as 1 over exponential of your incident light source. For example, if the incident light source is around 100, right, you just multiply 100 by 1 over epsilon, right? So at what distance do you get this value, right? In this case it would be around 37 value, 36%, 36 point something percentage, right? So at what distance from this starting point that it propagates through this solution do we get around 36.5 percentage of light source. But here you can see that that's the distance is nothing but 1 over alpha, and here you can see for very high absorption it comes around 30 absorption arbitrary units in this case. But what if for the smaller value of alpha? So you again draw a line over here, and you can see that it's around 80 arbitrary units approximately. Okay, so you can actually find the different penetration depth based upon what is the value of mu a or the alpha. Both are kind of the same thing. Okay, now both the definitions together. So you have the physics, that is the ratio of your transmitted intensity over the incident intensity, which is nothing but exponential of minus absorption coefficient into the distance of your cuvette, total distance, or how much light is going to propagate, and then it's also kind of at each instant you can actually find it out. So it's actually spatial version of your Beer-Lambert law. And in the another form in the chemistry, it's just the ratio of your output intensity of light divided by the input intensity of light, and it's nothing but you have, it just relates the concentration, right? The first one relates the absorption coefficient and the distance, how does it spatially vary, and in the second case it just tells about the concentration, just directly relates with the concentration. It doesn't talk about how it's actually spatially varying through a particular path of the light propagation, right? So these are the main two difference when you see both the definitions. Okay, for any material now, when you see any literature survey, you try to do this research in your field, and you will see that either mu a or you will get epsilon. You might not get always both of them, but both are could also be related. So you have a equation to actually relate both of them that you can see. And then for example, in this case, in the cases of tissue, there are many different tissue constituents. So you have epsilon of oxygenated hemoglobin. This is the absorption coefficient of your oxygenated hemoglobin. Then you have deoxygenated hemoglobin, and then you have cytochrome C oxidases, and then you have water, and then lipids, and then there could be many other materials. So all of them are having their own values of absorption coefficient, molar absorption coefficient as a function of wavelength. Okay. Okay, so looks good. So so here you can see that most of them are available. Now Beer-Lambert law is pulse oximeter, as you can see, and in the pulse oximeter you can see that we have the red light and an infrared light source, and then you have a detector, right? So again, in a tissue there are many different tissue constituents, like you have oxygenated hemoglobin, deoxygenated hemoglobin, methemoglobin, and then carboxy hemoglobin. But there are two main primary absorbers, and that is nothing but deoxygenated hemoglobin and oxygenated hemoglobin. And the values of epsilon at two different wavelengths, that is around 650 for the red and 950 for the infrared, are the two values that you already know. Okay. Now using this pulse oximeter, what do you find? You actually find the oxygenated saturation, that is SO2, oxygen saturation, and that is nothing but the ratio of your concentration of your oxygenated hemoglobin over the total hemoglobin. Now what is total hemoglobin? Is just addition of deoxygenated hemoglobin and oxygenated hemoglobin. So once you see your transmittance, that is nothing but the exponential of minus mu into h, which is equal to 10 power of minus epsilon c into h. And you can use this equation and you can write these two equations, right? So for first wavelength, so here you can see that you have epsilon 1, sorry, lambda 1, that is lambda 1 is for the first wavelength, that is 650 nanometers, and then you have lambda 2, the same equation that you write for lambda 2, that is nothing but for the second wavelength. Okay. Over here you can see that you kind of know all these values. You know what is the absorption, because you know what is the transmittance and transmitted light and incident light. So from mu a you can calculate from here, right? And you know what is the value of epsilon of Hb at this particular wavelength, right? I showed you just one slide back, right? You know what is epsilon at lambda 1. Similarly, you know epsilon of Hb at lambda 2, and then epsilon of HbO2 at lambda 2, that I just showed you one slide back. And this you can actually calculate out with this ratio, that mu a of lambda 1 and mu a of lambda 2. What we don't know is concentration of hemoglobin, deoxygenated hemoglobin from both this equation, and concentration of oxygenated hemoglobin in both the two cases. We don't know these two things, right? So now we have two equations and two unknown, and you can actually calculate out what is the value of deoxygenated hemoglobin and oxygenated hemoglobin, and then you just find the ratio of it out. Okay. For example, you get some values like 98%. Now, if you see the pulse oximeter again, what you see is that the first the red LED is switched on, okay, and then the infrared LED is switched on, and then both the LEDs are switched off. Now when both the LEDs are switched off, you will see that some light, because there is a background light source also which is incidenting, so you will see that there are, when both the LEDs are switched on, at that time also the detector is able to absorb some light, right? So this light is kind of ambient light source, and it actually gets removed from your algorithm that you use to detect your or you calculate your oxygen saturation. So you eventually get, once you detect, you get something like this pulse, and from this pulse this light that you see, the absorption that you see is not just because of the tissue, but there is also other thing. For example, you have pulsating arterial blood, which is what we want to find, right? You have absorption, the uniform absorption due to the non-pulsating arterial blood vessels, and then the absorption due to the venous and capillary blood, and there is absorption due to tissue. So these are the bulk absorption of various tissue components, but the most important thing that we are we are interested is the pulsating arterial blood that we want to quantify. So this thing again are kind of removed, both of these noises, one of these noises, and because of tissue constituent, both of them are kind of removed, and what you get, what you see over there is nothing but this one, and then finally you find something like a pulse rate, that is how much pulses per seconds are there, right? So that's what you can quantify. Okay, so that's how you actually can use Beer-Lambert law in real life application, which has been already been used to define the concentration of your hemoglobin, oxygenated and deoxygenated, and from there you can actually find the oxygen saturation. Okay, thank you.